Hello students, in the previous class we have learned about the preparation, properties and structure of the hydrogen. In this class or video we will learn about the preparation, properties and structure of the hydroxylamine. Okay. Uh, Now the formula of the hydroxylamine is NH2OH. We know very well that OH group is known as the hydroxyl group and NH2 group is known as the amine group. NH2 group is called as the amine group. We call NH2 group as the amine and OH group as the hydroxyl group. Hydroxyl group. So it is very easy to remember the formula of the hydroxylamine. If you know the formula, we can easily remember the name. If we remember the name, we can easily write the formula. So it is very easy to remember. Next we go for the preparation methods. Here we are going to study 3 preparation methods. Now in this slide we go for the first preparation method. Here hydroxylamine is prepared by the reduction of the nitrous acid. We know very well that nitrous acid formula is HNO2. Nitrous acid formula is HNO2 and nitric acid formula is HNO3. But here we have to remember one thing, that nitrous acid does not exist at room temperature. It decomposes or disproportionates to give the nitric acid and nitrogen gas. So that's why we have to prepare the nitrous acid whenever we require by using sodium nitrite salts. So here this is the sodium nitrite salt. So even though the name is that by the reduction of nitrous acid, here we are not going to use the direct nitrous acid. We prepare the nitrous acid by using the sodium nitrite. Okay, anyhow, now we go for the raw materials used in this first method. First one is the sulfur dioxide gas. Here sulfur dioxide gas, here in this case, act as a reducing agent. It acts as a reducing agent. We know very well that sulfur dioxide acts as the oxidizing as well as the reducing agent. So here sulfur dioxide is used to reduce the sodium nitrite ions. And the second one is the sodium nitrite. This is salt of the nitrous acid, so we call it as the nitrite. And sodium carbonate. And the fourth one is the barium hydroxide. So these are the 4 materials we use in the preparation of the hydroxylamine by using the nitrous acid. Next we go for the reactions. So you see the first reaction. Here in this reaction, nitrous acid, whenever we add the water to the sodium nitrite, it forms the nitrous acid in the aqueous solution. So that formed nitrous acid reacts with the sodium bisulfite. Here bisulfite is formed due to the reaction of the sulfur dioxide gas with the sodium carbonate. So I write that reaction. Look here. Sulfur dioxide gas we are using. So whenever we send the sulfur dioxide into the sodium carbonate aqueous solution, what happens means we get the sodium bisulfite NaHSO3 plus sodium bicarbonate. So we have such a type of two salts here. I write once again. Okay, sodium bicarbonate. So here this is a balanced equation. You can check it. Here on the reactant side, three oxygen atoms are there. On the product side also we have the three oxygen atoms. Two hydrogens on the reactant side, and on the product side also we have the two hydrogen atoms, and we have these two sodium atoms on the both sides and one sulfur atom on the both the sides. So this is the balanced equation. So this is not written in the slide, but we have to remember that sulfur dioxide, when passed into the sodium carbonate aqueous solution, it reacts with that sodium carbonate and forms the sodium hydrogen sulfide NaHSO3. Otherwise we call it as the sodium bisulfite. Sodium bisulfite, not sulfate, bisulfite. And second salt is the sodium bicarbonate. So we get such two salts. So this is the first reaction we have to remember. First reaction. Okay na? Then after that what happens means the sodium bisulfite formed reacts with the nitrous acid to form sodium salt of hydroxylamine disulfonic acid. Sodium salt of hydroxylamine disulfonic acid. Sulfonic acid means SO3H. So SO3H is known as the sulfonic acid. Okay, look here. Sulfonic acid group. So it is replaced. This H plus ion is replaced with the sodium ion. So we call it as the sodium salt. And we know well in hydroxylamine we have the two hydrogens, no? So here two hydrogens are replaced with this SO3H, this SO3. So that's why this salt is called as the sodium salt of hydroxylamine disulfonic acid. So if we replace two hydrogens with the two SO3H groups, then that becomes the hydroxylamine disulfonic acid. Look here. So this is hydroxylamine disulfonic acid, and here this is the salt. So this is known as hydroxylamine disulfonic acid. Hydroxylamine disulfonic acid. Okay. Here we get the so in the second step we get the sodium salt of hydroxylamine disulfonic acid. Okay now. Next let us look what happens in the third step. The sodium salt of hydroxylamine disulfonic acid is heated in the presence of dilute sulfuric acid at about the 87 degrees centigrade. Then what happens means this disulfonic acid salt decomposes and gives the hydroxylamine sulfonate salt. Hydroxylamine sulfonate. Okay na? And we get the sodium sulfate also. Sodium sulfate. Hydroxylamine sulfonate and sodium sulfate. And later on what happens means we take this hydroxylamine sulfonate and we react it with the barium hydroxide aqueous solution. As a result what happens, the sulfate ion reacts with the barium ions and forms a precipitate barium sulfate. It is the insoluble substance, so it precipitates out. As a result we get the aqueous solution of hydroxylamine. Here we are not getting the crystals. Here we get aqueous solution of the hydroxylamine. Now we go for the second step. Okay. In the second step, hydroxylamine is prepared by the reduction of nitric oxide. What is the formula of the nitric acid? Already we have learned that nitrogen forms of five types of oxides. Among them, NO is the nitric oxide. NO is known as the nitric oxide. So, here hydroxylamine is prepared by reducing this nitric oxide also. Nitric acid is different from the nitric oxide. Nit- Nitric acid formula is HNO3. Nitric oxide formula is NO. So this nitric oxide is reduced by means of tin and HCl aqueous solution. Tin and HCl solution. Here, tin reacts with HCl and releases the hydrogen, nascent hydrogen atoms. These nascent hydrogen atoms are useful in reducing the nitric oxide. So here we get the hydroxyl. If we use the excess of HCl, what happens means the HCl formed here, the hydroxylamine formed here reacts with HCl and forms hydroxylamine hydrochloride. Hydroxylamine hydrochloride. So here we get a salt. We don't get the pure hydroxylamine. So how we have to separate hydroxylamine from that salt means either by using sodium methoxide. So this is sodium methoxide. CH3ONA is a base, a strong base. Sodium alkoxides. Alkoxides are strong bases. Otherwise, we can use the sulfuric acid also. Sir, hydrogen sulfide. We can use the sodium methoxide or hydrogen sulfide to separate the HCl. As a result, what happens? We get the hydroxylamine NaOH and methyl alcohol. So, Cl is attached to the Na and NaCl separates out, and OH group will be attached to the H will be attached to the alkoxide group. As a result, we get methyl alcohol will be separated. So, here we get the aqueous solution of the hydroxylamine. So this is the second method. In the first method, we use the nitrous acid. So we can prepare hydroxylamine by the reduction of nitrous acid or by the reduction of nitric oxide, by the reduction of the nitric oxide. Then we move on to the what is the third step, third method. So third method is the electrolytic reduction method. Electrolytic reduction method. So here in this method we make use of the electricity to reduce the nitric acid. First method is the reduction of the nitrous acid. Second method is the reduction of the nitric oxide. Third method is the reduction of the nitric acid. So we are making use of nitric oxide as well as the nitric acid. So here 50% HNO3 is 50% HNO3 aqueous solution. We make use of the here 50% HNO3 aqueous solution, not concentrated solution. We are taking only 50% aqueous solution, and we add to the mixture of the nitrous acid and sulfuric acid. So that mixture contains 50% of the nitrous acid, 50% of the nitrous acid, and 25% of the H2SO4. So look here, 50% of the 50% and 25%. H2SO4 is about 25. So we prepare a mixture of 50% HNO2 and 25% H2SO4, and to that aqueous solution we add a 50% HNO3 solution. Then after we pass current into it. As a result, these reactions occur. Look at these reactions occur, and we get the hydroxylamine sulfonate, hydroxylamine sulfonate. Otherwise, we can call it as the hydroxyl ammonium hydrogen sulfate. Either way, we can call it as hydroxylamine sulfonate or hydroxylamine hydrogen sulfate. Like that, also we can call. So, first of all, what happens? Nitric oxide, nitric acid. Nitric acid is reduced to the nitrous acid. Then after nitrous acid is reduced to the hydroxylamine, and the form of nitrous acid reacts with the sulfuric acid and forms a salt, hydroxylamine sulfonate. And as we learnt in the first method, the hydroxylamine is separated from the hydroxylamine sulfonate. Barium hydroxide aqueous solution is added to that one. Barium hydroxide aqueous solution. As a result, barium sulfate precipitates out, and we get the aqueous solution of the hydroxylamine. So, in all these three methods, we get only aqueous solution. We don't get the crystals or anhydrous hydroxylamine. We don't get the anhydrous hydroxylamine. So, from the aqueous solution, we prepare the anhydrous hydroxylamine. The fourth method is also there. So, in the fourth method, hydroxylamine is prepared by reducing the ethyl nitrate. We know very well that nitrate ion formula is NO3 minus. So, here C2H5NO3 means ethyl nitrate. So, here we are discussing four methods. Fourth one is the reduction of the ethyl nitrate. So, here also we use a mixture of tin and HCl as the reducing agent. Tin and HCl as the reducing agent. Okay, na? So, here we get the ethyl alcohol along with the hydroxylamine. Okay. Next, we go for the physical properties. A hydroxylamine is a white crystal, and its melting point is 33 degrees centigrade, and boiling point is 68 degrees centigrade. And hydroxylamine is a deliquescent substance. That means it absorbs the moisture from the atmosphere, it absorbs the water and it changes into the solution, aqueous solution. All such substances which absorb the water from the atmosphere are called as the deliquescent substances. Deliquescent substances. And this hydroxylamine dissolves in the water, ether, and in the alcohol also. So it dissolves in the alcohol as well as in the water. Next, we move on to the chemical properties. First one is the decomposition reaction. Hydroxylamine is less stable. So, on heating, what happens? This hydroxylamine decomposes to give the nitrogen, ammonia, and water. This is a very simple reaction to balance, equation to balance. Here, on the product side, we are having one nitrogen molecule and one ammonia molecule. So, we have two nitrogen and one nitrogen. So, here we have to take the 3H2O, 3NH2OH. As a result, we get the 3H2O. So, it is very easy. Just we have to remember the products. We get nitrogen gas. We know the formula of the nitrogen gas, that is N2. And formula of the hydroxylamine is NH2OH. So, like that, we can easily balance the reaction. Next one is the basic nature of the hydroxylamine. So we know very well that nitrogenous compounds, that means the compounds which contain nitrogen in them, generally act as the base, because we know very well that on the nitrogen atoms one lone electron pair is there. Due to that, the nitrogen containing substance act as Lewis bases or alkalis. So here, due to that reason, hydroxylamine also act as the Lewis base. So as it is the base, it reacts naturally with the acids and form the salts. So look here. Here this is the basic equation that tells about the basic character of the hydroxylamine. Even though it is what is that Lewis acid, in the aqueous solution it acts as the Arrhenius acid, because here first of all it reacts with the water molecule and forms hydroxylamine hydroxide compound, which easily decomposes to give the hydroxide ions. So even though NH3 is hydroxylamine is a Lewis acid, in aqueous solution it acts as the Arrhenius acid, that we have to remember. Next, oxidizing nature. So the formula of the hydroxylamine is NH2OH, and we have to remember that all the substances that contain oxygen atoms in them definitely act as the oxidizing agent, there is no doubt, and all the substances that contain hydrogen atoms in them definitely act as the reducing agents, no doubt. So as the hydroxylamine is containing oxygen atoms in it, act as the what is that oxidizing agent. So look here, this is the base reaction that shows the acidic nature of the hydroxylamine. So this is very easy to remember. Hydroxylamine formula is NH2OH. When it decomposes, here oxygen comes out of the formula, so we get oxygen atom and we get ammonia. So it is very easy to remember. Hydroxylamine on decomposition gives the nascent oxygen atoms and ammonia. So when hydroxylamine act as oxidizing agent, we get the ammonia as the side product. So now we look on to the reactions in which hydroxylamine act as the oxidizing agent. Firstly, it oxidizes sodium arsenide Na3ASO3. In sodium arsenide, oxidation state of arsenic is +3. Here oxygen has -2, 3 into -2 -6, and sodium has +3 +1. So +1 into 3 +3. So definitely here arsenic will get the +3 oxidation state. And it oxidizes it to the sodium arsenate. In sodium arsenate, the oxidation state of the arsenic is +5. So here arsenic is oxidized from +3 to the +5. So it oxidizes sodium arsenide to the arsenate. In the similar way, it oxidizes ferrous hydroxide to the ferric hydroxide. Ferrous hydroxide means ferrous ions means Fe plus 2 ions. We know very well that ferric ions means Fe plus 3. So this is also very simple to balance the reaction. Here one water molecule reacts with one oxygen atom of the hydroxylamine and forms 2 OH minus ions, 2 hydroxyl ions. So you have to take the 2 ferrous hydroxide molecules, and here we have write the 2 ferric hydroxide molecules. So these reactions are very simple to balance. Okay na? Next we go for the reducing nature of the hydroxylamine. So as already we have learned that all the substances that contain hydrogen atoms will act as the reducing agent. So the reducing nature of the hydroxyl can be explained by writing two types of reactions. So look here my dears, this is the first reaction and this is the second reaction. In the first reaction what happens? Hydroxylamine is gaining oxygen atoms from the other substances and it is decomposing or oxidized to give N2O. N2O means nitrous oxide and water. And the second type of oxidation, what happens? Hydroxylamine decomposes to give the same nitrous oxide and water, but here we are getting the hydrogen atoms, nascent hydrogen atoms. So hydroxylamine act as the reducing agent either by accepting oxygen atom or by giving the hydrogen atoms. It acts as reducing agent by accepting oxygen atoms from the other substances. It acts as reducing agent by donating or giving hydrogen atoms to the other substances. In both the ways, we can justify the reducing nature of the hydroxylamine. Okay, now then we move on to the reactions. So, the hydroxylamine reduces the failing reagent. Generally, we use the failing reagent in order to identify the monosaccharides. That means glucose, fructose, like that. Saccharides are known as the monosaccharides. Like that, we have many monosaccharides, arabinose, ribose. So, plenty of monosaccharides are there. So, monosaccharides are identified by using the failing reagent. Failing reagent is also used to distinguish between the aldehydes and ketones. So, here in failing reagent we use the two reagents, failing 1 and failing 2. Failing 1 and failing 2. Failing 1 is nothing but alkaline copper hydroxide, copper sulfate. Alkaline copper sulfate solution is known as the failing 1. Failing 1. Yes. Sorry for the disturbance. Yes, yes. Okay. Right. Right. Ah. And failing 2 is failing 1 is alkaline copper sulfate and failing 2 is alkaline solution of Rocelli salt. Rocelli salt. What is Rocelli salt? It is sodium potassium tartrate, SOPOTA or SAPOTA. With this acronym we can easily remember failing 2 reagent. Failing 2 reagent is alkaline solution of Rocelli salt. Then what is Rocelli salt means? It is a sodium potassium tartrate. You know very well that tartaric acid is present in the tamarind. Okay. So actually it is a complex reaction, but for convenience, when these two reagents are mixed, we get a blue color solution. That is a complex compound, but for convenience, we represent the failing reagent as the cupric oxide, Cu2O. We know very well that Cu plus 2 ions have the blue color. So when we mix failing 1 and failing 2 reagents, we get a blue color solution. That is nothing but, in a simple manner, we can say it as the cupric oxide. When cupric oxide is treated with the hydroxylamine and heated, we get a red color precipitate. That red color precipitate is nothing but cuprous oxide. Cuprous oxide. So this is very simple equation to balance the reaction. Okay, na? Here I have shown here two methods to remember the reaction between the failing reagent and the hydroxylamine. So in the first equation, hydroxide ions are not shown. Simple reaction is given. Even the products are same, second reaction is written in the different manner. Already I have told that failing reagent is a alkaline solution. So in the second step, hydroxide ions are shown. Okay, so here in both the ways we can write the reaction. Okay, na? Okay, this is also very easy to balance. Here the wrong formula is written for the cupric oxide. Cupric oxide formula is not Cu2O, it is CuO. Sorry, it is CuO. Okay, na? So when 2 CuO converts into the Cu2O, they give one oxygen atom. So by this equation, we can easily write the balanced equation. Okay, na? Right. And from the hydroxylamine, look here. Here, look at this is the reaction with hydroxylamine can be easily written by considering the first reaction here. So by this reaction, we can easily write the reaction with the failing reagent. Okay, na? Right. Next one is the reduction of the Tollens reagent. Tollens reagent is also used to identify the monosaccharides, and it is used to distinguish between aldehydes and ketones. Tollens test is given only by aldehydes. Ketones do not give the Tollens test. Then what is Tollens reagent? We have to understand. Tollens reagent is a mixture of the silver nitrate and ammonium hydroxide. So we call it as the ammonical silver nitrite. Ammonical silver nitrate is known as the Tollens reagent. Ammonical silver nitrate is called as the Tollens reagent. Okay, na? Right. So we can write the reaction in the two ways, so that are shown here. Okay, na? Yes. So in the first reactions, in the first equation, simple way, the products and reactions are shown. In the second method, hydroxide ions are also written. In either way, we can write the equation. Next, here this reaction of the hydroxylamine with the Tollens as well as the failing reagent can be easily balanced by using the first step of the basic equation. Okay, next, here this hydroxylamine reduces the mercury chloride also. Firstly, as I forgot to say that in the Tollens reagent we get the silver coating on the walls of the test tube. So that's why this Tollens test is also known as the silver mirror test. Tollens test is also known as the silver mirror test. Okay, that we have to remember. And it reduces the mercury chloride also. When hydroxylamine reacts with the failing reagent, it gives cuprous oxide, a red color precipitate. And whenever it reacts with the Tollens reagent, it gives the silver metal. And okay, in a failing reagent, in reaction with the failing reagent, we get the compound and metallic compound, and in the reaction with the Tollens reagent, we get the metal as the precipitate. But whenever this hydroxylamine reacts with the mercury chloride, first of all, mercury chloride is reduced to the mercurous chloride. Mercury chloride formula is HgCl2. Mercurous chloride formula is Hg2Cl2. Which Hg2Cl2 is a white. This is a white color precipitate. White color. Look at this is a white color. Mercurous chloride is a white color precipitate. Immediately after what happens, this mercurous chloride react with again hydroxylamine and gives a black color PPT, that is mercury liquid or the mercury. So here we get the mercury in the form of the black color. Sometimes chemically degraded metals appear in different colors. For example, we can prepare the gold in various different colors. Okay, na? So like that, here we get the mercury in the black color. So that is the point we have to remember here. So yeah, look at this is the simple equations used to write the reaction with mercury chloride, and we go for the complex reactions. Look at this, these are somewhat tough reactions to remember. Okay, so in either way we can write these reactions. And here hydroxylamine reduces the chlorine to the chlorides, and not only chlorine, it reduces halogens to the halides. This is also very simple reaction to balance. If we practice once, we can easily write them. Okay, now right. Here hydroxylamine also behaves as a base. I have already told you that during the preparation that on the nitrogen atom of the hydroxylamine, lone electron pair is present. Due to that, this hydroxylamine reacts with the acids and forms the salts. For example, it reacts with the HCl and forms the hydroxylamine hydrochloride, and with the sulfuric acid forms the hydroxyl ammonium sulfate. So here we get the salts due to the basic nature of the hydroxylamine. Now hydroxylamine shows the participates in the condensation reactions also. For example, it reacts with the aldehydes and ketones and forms the condensed products. So such condensed products here are called as the oxides. Condensed products of hydroxylamine are called as the oxides. So here it reacts with the acetaldehyde and forms acetaldioxide. This condensation reaction take place in the presence of the acids, H plus ions. Look here. So while writing the name of the product, we have to mention the reactant's name also. For example, here acetaldioxide. In the similar way, ketone and acetone also reacts with the hydroxylamine and forms a condensed product. This is known as the acetoxide. So acetaldehyde forms acetaldioxide, acetone forms acetoxide. This reaction is used, this condensation reaction of hydroxylamine is used to prepare the polymers like nylon 6. To prepare the nylon 6, Hydroxylamine is allowed to react with the cyclohexanone. This is cyclohexanone. Look here, cyclohexanone. So here we get a oxime. Here we get a oxime that is known as the cyclohexanone oxime. Then after what happens is the cyclohexanone oxime is treated with the oleum. Oleum means concentrated sulfuric acid, and we know its formula, that is H2S2O7. So H2S2O7 is known as the oleum. So oleum ions provide the H plus ions. In the presence of the H plus ions, oximes undergo Beckmann's rearrangement. Here, this one is known as the Beckmann's rearrangement. In organic chemistry, we get this one, Beckmann's rearrangement. So cyclohexanone oxime undergoes rearrangement reaction, that is Beckmann's rearrangement, and forms amide. In Beckmann's reaction, oximes form amides. So here we get a cyclic amide. That cyclic amide here is called as the lactam. Then after this cyclic amide or caprolactam is subjected to the polymerization. So due to that polymerization, here we get the nylon 6. Okay na? That point we have to remember. Okay na? Here the number 6 indicates the number of the carbon atoms. Here hydroxylamine has the two types of structure. Structure 1 and structure 2. In structure 1, nitrogen is attached to the two hydrogens and one hydroxyl group, and all are simple covalent bonds. Whereas in the structure 2, nitrogen is attached to the 3 hydrogen atoms and 1 oxygen atom. The bond between nitrogen and oxygen is a coordinate covalent bond. So here, two types of structures are proposed for the hydroxylamine. And moreover, we have to remember that structure 1 exists as the two isomers. One is the cis and the other one is the trans isomer. Now we have some evidences against the in the support of the structure 1 as well as in the support of the structure 2. So for the both the structure we have the evidences. Look here, we can prepare hydroxylamine by using the nitric acid. By the electrolytic reduction of the nitric acid, we can prepare the hydroxylamine. Here we know already the structure of the nitric acid is well established. Here in nitric acid, one hydroxyl group is attached to the nitrogen. In the similar way, one hydroxyl group is present in the hydroxylamine also. So this one confirms the structure 1 for the hydroxylamine. One more evidence is that hydroxylamine reacts with the nitrosobenzene. This one is C6H5NO. This is known as the nitrosobenzene, and forms isodiazobenzene. In isodiazobenzene, a nitrogen atom we have one hydroxyl OH group. So in order to get this isodiazobenzene, the structure of the hydroxylamine should be NH2OH. That means structure 1. It should have the structure 1. So by considering the structure 1 only, we can explain the this reaction. Okay, we can explain this reaction. Okay, so that these two are the evidences in the support of the structure 1. Now we have the evidences in the support of the structure 2 also. Here already we have learned that hydroxylamine is prepared by reducing the nitric oxide. So already we know the structure of the nitric oxide. Nitric oxide formula is NO. Okay. So again, we can write this as the coordinate in the form of the coordinate covalent bonds also. NO like this also we can write. So if the structure is not like that, we can't get the uh, hydroxylamine by reducing the nitric oxide. So the preparation of hydroxylamine by using nitric acid tells or is the strong proof for the structure 2 of the hydroxylamine. Second one is that hydroxylamine oxidizes titanium trioxide and forms titanic acid H2TiO3 and gives ammonia. So the formation of ammonia in this second reaction confirms that hydroxylamine also has the structure 2. So now we can say that hydroxylamine exists in the two different forms. Okay, now. Okay, thank you.